Welcome to the Physics 11 show with your host, Kelvin Dueck. And we're live.
Okay. Distance, ready? Number one, let's mark this really quickly. Mark your own. 1A, how far is the truck from its starting point after 10 seconds? What's this question asking me, Atla? How what? Far. It's asking me for distance. Now, where does distance appear on this graph? Is it the slope? Everybody say no.
No.
What is it on this graph? What's on the y-axis? What's on the y-axis? The distance is the height. On this particular graph, the distance is the height. So how far are we from the starting point after 10 seconds? That far, right there. How far is that? 300. Units? Meters. How far is it after 15 seconds? Also 300 meters. Oh, I guess I stopped for a little bit. How far is it after 30 seconds? 200 meters? After 43 seconds, I got to kind of eyeball it, but that's right about there. Right around there. I'd take 650, 650. As soon as it's between squares, we're doing a rough guess. I'll go with 650 meters. What about at 50 seconds? 800. Okay. What's the truck's velocity in each of these intervals? How can I find, and this is really the point of this, how can I find the velocity if it's a distance time graph? What?
The slope.
What?
The slope.
The slope. So in interval A, I'll call that velocity of A. That's a good notation, I think. The slope is the rise over the run. Again, do not say this. This is what I saw on the test, Emma. Don't go, oh, the rise is 3 and the run is 2. You're counting squares, not the scale. You have to count the scale. I think the rise is from here to here. I think the rise is 300, isn't it? And the run is 10 seconds. I think the velocity is 30 meters per second. I think the velocity of section B, 0. I think the velocity of section C, negative. We're heading backwards. I can tell you that. Let's see. How high am I when I started? 300. How high am I when I ended? 200. I think the rise is 100. I think the run is 10 seconds. I see about 10 of you writing stuff down. This was homework, humans. I gave you 2 classes. Hey, in your head, McKinley, what is 100 divided by 10? What would negative 100 divided by 10 be then? What does the negative mean? Traveling backwards, turned around, coming back. I don't know. I need more information, but I can tell you that's occurring. What about interval D? Okay, interval D. From here to here. What's the rise? Well, it looks like I end up 600 high. I start out 200 high. I think the rise is 400. What's the run from here to here? It looks like another 10-second interval. Holy smokes, Sasha, I can do this in my head too. At least I can. With or without the hair. Okay. 40 meters per second. By the way, Jeff, what's faster in my data? Velocity A or velocity D? What answer is bigger? What answer is bigger? Velocity A or velocity D? What answer is bigger?
40 meters per second.
Yeah, with authority, confident. I'm giving you a nice low ball. Which one's bigger?
40 meters per second.
So which line should be steeper?
D.
Should be. Let's double check. In other words, I knew ahead of time that I'd better get an answer bigger than 30. If I didn't, I've either done the slope of this one wrong or I've done the slope of the other one. There are some built-in error checks is what I'm saying here, right? And location E, still positive. Interval E. The rise is 200. The run is 10. 200 over 10, 20 meters per second. I would have no problem turning that into some kind of a quiz or a test question or something like that, giving you a similar kind of a graph and saying, interpret it for me. Or I could even say, briefly describe the kind of motion, like in number 3. When I'm talking about describing the motion, here's what I'm looking for. Moving forwards, moving backwards, speeding up, faster, slower, or at rest. So how many different intervals are there in this first graph here? 2. In the first section, describe the motion. What about this second section? Sorry? Direction first, please. But? By the way, I have to correct you just a tiny, tiny, tiny bit, Joanne. Not slowing down, because slowing down would mean that it was still getting shallower, because in the process of slowing down, slowed down already, because that speed didn't change either. Once it changed. And this is kind of weird motion. We don't move in real life this way, but what this is saying is, I guess, going really, really, really fast, instantly slowed down, instantly, and that's why it's kind of a jagged, and this is why we said curves are more realistic, but the math is tougher to deal with, so we'll try and deal with linear whenever possible. What about the second one here? How could you describe that?
Moving forwards.
What about that?
Stop.
Ooh, someone used a physics word. Stopped, but yeah, at rest is usually what we say in physics. Ooh, this third one is interesting. Nice, he says. Nice. Here, here, and here. What's happening in that first interval? Direction, first of all, please. Forwards and speeding up. How do I know it's speeding up? What's happening to the steepness?
It's increasing.
Increasing. Yeah, increasing. What about the middle section?
At rest.
Rest. What about the third section? Direction?
Forwards.
Faster or slower than the original? Well, definitely faster than that section because it's steeper. That's why I asked you that question earlier, right? There's a nice visual. I'm eyeballing this. Does this and this look like the same steepness? I need graph paper to be sure, but Rob, I think so. So I'm going to say this. Forwards, how about this? Max speed, the same as what you maxed out from the previous one. I don't know. I'd give you some numbers if I really wanted to ask that particular graph. You'd actually be able to calculate the slope and be able to say, oh, 12 meters per second. Turn the page. Describe the motions represented by each of these. As the speed is changing, state whether it's increasing or decreasing. So, first graph. Direction. Forwards. And what? What's increasing? Forwards. Now, I'm going to pull out the physics word. We have a physics word for increasing speed. Begins with letter A. Let's start using that. Accelerating. What about here? Direction. Forwards. Okay, I would take decelerating, although that introduces a new, first of all, I'm going to say forwards. Here's what I'm going to say because I don't want to have a brand new word and I'd like to bring in some mathematical context. Negative acceleration. Isn't that what slowing down really means? In the opposite direction of what we define as positive. That is decelerating. Ooh. What about here? Direction.
Forwards.
The whole time? What's going on with that shape? Sort of. That shape.
It starts accelerating, but then starts decelerating.
Accelerates. Then negative acceleration. Decelerates, slows down. I take all of those, but I'm saying, Kyle, let's get comfy with some physics words. Okay. Ooh. What's that? This first one. What would you say? Moving forwards, steady speed or changing? Steady speed? Do you think looking at that graph fast or slow? Well, it depends. There's no scale, but I would assume steeper probably meant fairly quick, although maybe not. Maybe this was a really slow motion time-lapse scale on the x-axis, and so time's not moving very fast. I don't know. What's the middle section? At rest. Bottom section. Okay. If this right here is 10, what's the distance? Total distance. I heard it. 20, there and back. What's the displacement? 0. Right? Because your change in position was you ended up back where you started from. What's this middle graph doing? Forwards. Turned around. Forwards again. Turned around. Forward. Can you think what that might be a graph of? Is there something you've been in or seen that does that? What was that? Why can't that be a roller coaster? Probably. I think a roller coaster, your displacement is 0. You should end up on the same height as you started from. Because you do get off where you get on. At least in all the ones I've been on. Yeah? Right? I think if that had gone all the way down and touched, then we might have a discussion, at least possibly. Is that okay, Darian? Or no? Okay. Now, if it was just a chunk of a roller coaster, maybe. But I think it's a better example. Go ahead.
It could be kind of like the, what's that right called? The one from Playland, the Crazy Beach Party, where it's constantly swinging back and forth.
You guys are way overcomplicating it. Think 6- and 7-year-old. Think playground. What?
Swing.
Swing? How? Oh, now as a distance, we're talking vertical height. Do you start out on the ground? You get on the swing. I guess in this case, it looks like because right away you're getting good velocity, you know what? Someone's giving you an underduck. Do we still call them that?
Yeah.
Or, okay. It's called that when I was a kid too, okay? Because you get to your maximum height, and then you swing back towards the ground again. Maximum height. But you don't ever touch the ground on a swing, and that's why this graph never touches the ground. Could be a swing. The only thing I don't, well, no, I was going to say if you're not pumping, then the height should be a little less, but you could pump and match exactly the original underdog. A swing might be an example of that. I'll argue that that's impossible. I don't know, there's others, but I always like to try and puzzle out, is there something that I can match that graph to? Sorry, little nerd moment. Hey, what's happening here? Start off going what direction? Forwards? Speeding up or slowing down? Oh, thank you for saying thank you. Thank you for serving your... No, not thank you for... Get out of here.
Thank you for letting me take my detention.
Yeah, whatever. I'm too nice. speeding up right here because initially it's getting steeper, but what's it doing here? So I think this is actually how a lot of cars work. When you floor it, the initial acceleration is big, but then you don't accelerate quite as fast. So maybe this is a car at a red light. Floor it. Lots of acceleration. Level off. Ooh. What's that mean? Stops. And then traveling. Okay, my car example I don't think makes sense to me unless I can think of a situation when I'm driving where I do this. I don't. What could that be a graph of? See, I was going to say stop sign, but you don't go reverse. And there's definitely a reverse component there, is there not? You don't go reverse at a stop. At least I don't. Do you have your N? Be afraid. Yeah. Sorry?
Rolling the ball uphill and then
Rolling the ball up a hill and then back down. Let's see. When you roll the ball up the hill, it's got its maximum speed, but it starts to slow down. It comes to a stop. It starts to speed up going backwards faster and faster. I almost like that. The only parts I don't like is, to me, it almost looks like after you let go, it got steeper for a second. It got faster for a second. So, or you could argue that was part of the holding on of the ball during the push. Okay, fair enough. Good job. Last one, I think I have an actual answer key for, so I'm not going to video it. So I've thrown those answers up and online. Those of you that are watching at home, we didn't go through every answer on the video. The answer keys are online. Key idea from last day. What's the slope of a distance time graph? Velocity. What's the slope of a velocity time graph? Acceleration. Acceleration. Do you have to memorize that? You can actually figure it out from the units. You may recall last day I did this. I said, you know what? If you give me a distance time graph and you say, what's the slope? I actually just look at the units. And I say a slope is rise over run. The rise is meters. The run is seconds. The slope is meters per second. Hey, that's the velocity. If you give me a velocity time or speed time graph, hey, what do we measure speed in? Meters per second. What do we measure time in still? If I go rise over run, it's going to be meters per second divided by, or over, seconds. Now, this is a three-level fraction, and most of you suck at three-level fractions. But what I'm going to tell you is, when you take a fraction and you divide it by a number, that's the same as having both of those on the bottom. Except, would we write S times S, or what's a nice, clever, short way to write that?
S squared.
I'm telling you, if you go rise over run, you're going to get meters per second squared, which you learned last year measures what? Acceleration. You can memorize the graphs, go ahead. But for what it's worth, it can be derived in about 15 seconds of brain time, and so I've chosen to use my brain's memory capacity for other stuff, in particular for memorizing this trick, this idea that I can divide units to find slope. Then I can almost always figure it out. If I can't, well, I have other strategies that we'll talk about. So, we were looking at this example here, where we had an object with an acceleration of 1.25 meters per second squared to the east. And we said, what if it starts at rest? What if we're initially moving west? So we looked at actually 3 examples, and we said, you know what? I noticed that I can hopscotch my way there. And what I said to you last day was, we'd like to reach a point where we don't need to do this the long way. So I did say pause here. I said find the slope and interpret the graph. Do I want to do this? Do I want to do this? Well, that's got yucky decimals. I think I'm going to skip this example. What I am going to do is say, hey, that's important. Velocity is the slope of a position time graph. Acceleration is the slope of a velocity time graph. Example 6 says, describe the motion depicted on this graph and then try and fill in the missing graphs. Okay, can you tell me, I'm seeing kind of 3 sections, yes? First section, what's happening? Direction.
Forward.
Steady speed or accelerating in the first section? In this section right here, I heard someone say accelerating. Can you tell me why it can't be accelerating? How do you know it's going at the same speed? All lines are straight, Captain Obvious. I need more than that. It's a constant slope, which means, by definition, it's a line. Forwards, steady, velocity, no acceleration. Heck, I'll even call that interval 1. I'll call this interval 1, interval 2, and interval 3. So interval 1, doing that. What about interval 2? Direction.
Forwards.
What can you tell me about its speed? Changing, increasing, decreasing, staying the same? What?
Increasing.
Why increasing? You're right.
Because the slope's steeper.
Ah, the slope is getting steeper. So what's the fancy schmancy word for increasing speed? Three, direction. Sorry? Forwards, yeah. What else can I say?
Steady velocity.
How would you compare 3 and 1? Which one's faster?
3.
Oh, so I'm going to go steady velocity, comma, faster than situation 1. Okay. Underneath that, it wants us to graph a velocity time graph. So section 1, what will that look like as a velocity time graph? Positive or negative, first of all? Because you're going forwards. If it was negative, if it was going backwards, I'd draw it below the x-axis, but we didn't. Curve or straight line, and how do you know?
Straight.
Why straight?
Steady velocity.
I think section 1 looks like that. Okay, Shaq, I'd take higher or lower, but what I'd be looking for is a horizontal line, because that's saying a positive, constant velocity. What will 2 look like? What will 2 look like? Sloped line?
Positive slope.
I think it's going to look like this. It's speeding up, it's speeding up, it's speeding up, and now its new speed is whatever height that is. I don't think the acceleration slope is curved. I think it's a steady acceleration, but I think it's a changing height. There's your new speed now. What about line 3? Let's go higher. Is this right?
No.
Why can't that be right?
Because it's steady velocity.
Oh, it's a steady velocity, you say. So what line on a velocity time graph, what does a steady velocity look like?
Zero slope.
Horizontal line. That would be a positive, steeper slope than that on a distance time graph, position time graph, but on a velocity time graph, there's my interpretation. Got to really think carefully. It's very easy to trip on our brain. Hopefully we're kind of getting the hang of it. Yeah? Did you say we want to do acceleration? You did! Let's do acceleration right underneath here. Can you tell me, in section 1, trick question, what's the acceleration? What?
0.
So what would that look like on an acceleration time graph? That would look like a line that was 0 high, because on this graph, your height is your acceleration. How do I know, Kyle? Because what's on the y-axis here? A, yeah, acceleration. Ooh, that middle section, are we accelerating?
Yes.
Positive or negative?
Positive.
Changing or constant? I think constant, although I'd really need calculus to prove it. I'm going to tell you it is constant. Wait a minute, Mr. Dueck, it can't be constant. The line is curving. The position line is curving, but the velocity line is constant slope, straight. Positive. I don't know, about that high. Could be lower, could be higher. I have no numbers. But I'm telling you, it's above 0. What about section 3?
0 acceleration.
Some deep thinking here, Manny. You really got to puzzle this through. And if you're finding this confusing, congratulations, you're normal. This is a tough concept. We are eventually going to break away from the graphs because while on one hand visual is nice, on the other hand, sometimes being able to just crunch numbers is nice. And when I see you Tuesday, we'll start crunching numbers. Let's keep going though. We may even get to it today. Example 7 says, consider the velocity time graph below. Describe the motion depicted on the graph. B says, at what time does the... Okay, let's do A. I'm going to divide this into section 1, section 2, and I have a feeling where it goes below might be important, so I'll call that section 3. The other thing I need to notice very, very carefully here, Trevor, what kind of a graph is this? What's on the y-axis? Ah, so I got to shift my thinking. The slope is not velocity. What's velocity on this graph? Not the slope, but what?
The y-axis.
How high? The y-axis, yeah. What's the slope of this graph? Acceleration. Oh, okay. So, can you tell me, section 1, what's going on there? Steady velocity forward, is he correct?
No.
How fast are you going at time 0? How fast are you going at time 3? You know what? Let's add some numbers. Look up. Let's call this 5. Let's call this -5 meters per second and seconds. And I'm not sure if it looks like it on yours. Let's assume that that peak is supposed to be the same height as that hash mark, and that bottom is supposed to be the same height as that hash mark. I printed this so often from this. Here, this was originally typed in Word 95 for Mac. So what are we? 2013 for PC. The diagrams are slowly getting warped, and I'm probably going to have to slowly start retyping them, but it's not a job I look forward to, so I'm trying to get them to last as long as I can if I can. So if you're wondering, it got a little squashed. We'll live with it. Hey, how fast are you going at time 3 seconds? One, 2, 3 seconds right there. I think 5.
Mm-hmm.
So, do you want to retract your statement? You said steady speed. Ah! What way?
Forward.
And I'm going to say traveling forwards. Mr. Dueck, if you're accelerating forwards, doesn't that mean you're traveling forwards? I don't know. Let's find out. What can you tell me about section 2? Slowing down? You know what? Let's call it accelerating backwards or negative acceleration. Traveling which way?
Forwards.
Wait a minute, how can I be traveling forwards if the slope is downhill? Because the slope is not the velocity here. What's the velocity on a velocity time graph? How does it appear? It's the height. Is your height still above 0 in section 2? That means that you're still moving at a positive velocity. Forwards. Still moving forwards. What about section 3? Still accelerating what? Backwards. What's your velocity direction? How do you know backwards? What does this look like? Something like this, I think, if I visualize it. Part A was describe the motion. There. Let's answer. I think I can do B down here somewhere, I hope. B, at what time does the velocity have the greatest value? Where does velocity appear on this graph?
Y-axis.
Height? Oh, when is it its highest? At t equals?
3 seconds.
At what time does the acceleration have the greatest oh, by the way, it said greatest positive value because it could have been, maybe it went negative faster, backwards faster. So greatest positive value. C, at what time does the acceleration have the greatest, listen close, positive value? Between what times? By the way, what is the acceleration between 0 and 3? What's the slope? What's the rise? Five. What's the run? There's the actual acceleration then. Positive 1.6, I think 5 divided by 3 is 1.66666666, yes? Okay. I knew that. I was just trying to make people feel better if they couldn't do it in their heads. Sorry. At what time does the position have the greatest positive value? When are you furthest away from home? At 3 seconds?
No. 3 to 7. 3 seconds and 7 seconds. 5 to 8.
Let's find out. Watch. Did I convince you with my stupid drama there? But yes? I think you can make an argument. So, 5 seconds. So, bonus question. I haven't covered this. Where does distance appear on a velocity time graph? It's not the slope. What's the slope of a velocity time graph? Accelerate. So it's not that. What was that? the area. It's the area. And in fact, when you get to Physics 12, those of you that take Physics 12, you'll be asked to interpret graphs, and Kyle, I'll either say, tell me what the slope means, or I'll say, tell me what the area means. Put your pencils down for a second. So let's suppose you had a graph, velocity versus time. What are the units for velocity? What are the units for time?
Seconds.
Suppose I gave you a graph that looked like that, and I said, tell me what the area means. How do you find the area? This isn't a rectangle, but let's pretend it is. What's the area of a rectangle? Length, what? Width? Did you say times? Did you say times?
Yeah.
So for slope, we divide rise over run, and look at the units. You know what we do if they ever ask me to interpret the area? I times the units. Because if I go meters per second times second, what happens to the S's? You see it? What do they do, Manny? And what units are left behind? And what's meters a measure of? It's got to be. You can memorize all this, but I'm giving you some good tricks right now, especially those of you in chemistry. I think they do graphs in chem as well. Little tricks of the trade. If it's slope, divide the units carefully. If it's area, whatever the shape is, temporarily pretend it's a rectangle, times the units. That'll tell you what it is. Won't tell you the answer. If it's like, I don't know, this is called a trapezoid, and there is an equation for the area of a trapezoid. You could figure it out, but I can tell you at least what it means. It's got to be distance. It's got to be distance. Tricks of the trade. Answer the following on a separate piece of paper. You know what? I think you can do these on this homework. I'm going to say, number one, we're dropped object. We're starting at rest. So you can already fill in that your initial velocity is 0. The acceleration is negative 9.8. So see if you can fill in number one. Instead of graph velocity versus time, try and sketch it. Actually, you know what? I'm going to nuke B. I'm going to say 1A. Scratch out B. 2 is good. Yeah, those are tricky. What happens to the motion of an object if... Okay, I'll live with 3. 4. I crossed out the distance questions because I'm not going to test you on it, but when B and C are asking you for displacement, it would be the area underneath that section. Big deal. 6 is good. Oh, 5 is good, sorry. Yeah, velocity at 3, that works. Maximum velocity, that works. Acceleration, yeah, that works. Average, that works. You got the answers there too. Good, 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 good. 6, I said. 7 is good. And I got a couple of, I think I have a take-home quiz. Give me a second here. Pretty sure I do. You don't want to put a marker there? Oh well, there is now.